We're absolutely surrounded by data. But here's the thing. We almost never have the complete picture, right? We get these little snapshots, these individual points, but there are always huge gaps in between. So how do we fill them in? Well, that's exactly what we're diving into today, the amazing mathematical art of connecting the dots. Just think about this for a second. Let's say you check the temperature at 1 p.m. and it's pretty warm. You check it again at 3 p.m. and it's cooled down a bit. Okay, great. But what about all that time in between? What was the exact temperature at, say, 2:15 p.m.? We've got the data points, but the answer we need is hiding somewhere in that gap. And this isn't just about the weather, not at all. This problem of the gaps is literally everywhere. How does a character in a video game move so smoothly between different poses? How does a scientist figure out the rate of a chemical reaction with only a few measurements? The key information, the really important stuff, lies in that unknown space between the points we actually have. So, how do we solve this puzzle? We use an incredibly powerful tool called an interpolating polynomial. The best way to think of it is as a custom-built formula. Its one and only job is to draw a perfectly smooth curve that hits every single one of our data points, guaranteed. It is, for all intents and purposes, our ultimate dot connector. Now, here's what's so cool about this. This technique really has two main jobs. First, it helps us build a complete picture when all we have are those few little snapshots. But second, and this is a real game changer, it lets us take some ridiculously complicated function and swap it out for a much simpler polynomial that's way easier to calculate. So we're not just filling in what's missing, we're also simplifying what's too messy to handle. So there are a few ways to build these amazing functions, but today we're going to focus on one of the most elegant and, I think, intuitive ways to do it, the Lagrange method. Seriously, think of it like a recipe. You just follow the steps and you get a perfect fit polynomial every single time. Let's start super simple with just two dots. This is what we call linear interpolation. So we take our 2 points, and for each one we figure out something called a weighting function. This basically decides how much influence each point gets along the line. Then you just blend them together and boom, you get a perfectly straight line connecting them. Okay, so what in the world are these weighting functions actually doing? This is where the dimmer switch analogy is just perfect. Imagine you have 2 dimmer switches, one for each of your data points. When you are standing exactly on top of your first point, its switch is cranked up to 100%, and the other one is totally off, at 0. As you start moving toward that second point, the first switch dims down while the second one starts to brighten up. It's this clever little handoff that guarantees our line passes perfectly through both points. All right, enough theory, let's get our hands dirty. Here's a nice, simple problem from our source material. We know that when x is 2, the function's value is 4, and when x is 2.5, the value is 5.5. So the big question is, what's the value when x is 2.2? So we use that Lagrange recipe to calculate the specific dimmer switch functions for our 2 points. And when we combine them and simplify everything, all that math boils down to this beautifully clean formula. P of x equals 3x minus 2. That right there is the one and only straight line that connects our 2 dots. And now for the magic. We take our target, 2.2, and we just plug it into that formula we built. So 3 times 2.2 minus 2 gives us 4.6. And just like that, we found our missing value. We successfully navigated the space between our data points. Okay, connecting 2 points with a straight line. Pretty cool, pretty straightforward. But let's be honest, the real world is rarely a straight line, right? It's full of twists and turns. So what happens to our model when we don't just have 2 points, but a third one? This is where we level up. We go from a simple straight line to a beautiful, smooth curve. With 3 points, the Lagrange method doesn't give us a line, it gives us a parabola, what's also called a quadratic polynomial, and it's the only parabola that will hit all 3 of our points perfectly, which lets us model much more complex behavior. All right, here's our next challenge. At x equals 0, our value is 1. At 1, it's 3, but then at 3, it jumps all the way up to 55. Whoa. A straight line is definitely not going to work here. We're going to need something with a little more curve. So we run the exact same Lagrange recipe, just with 3 points this time instead of 2. The math's a little heavier, but the principle is exactly the same. And what pops out? This quadratic polynomial. See that x squared term in there? That's what gives us the curve we need. and you can go ahead and test it. This formula will perfectly nail all 3 of our original data points. Now, the Lagrange method is fantastic. It really is. But it's super important to zoom out for a second, because in the real world, we have to think about accuracy, and it's good to know that Lagrange isn't the only tool in the shed. For instance, there are other approaches, like Newton's method. It actually builds the very same polynomial as Lagrange, but it does it using something called a divided difference table. The big advantage here is efficiency. Let's say you get a new data point tomorrow. With Newton's method, it's way easier to just update your formula instead of having to start all over again from scratch. And this brings us to a really crucial idea: error. Because our polynomial, as amazing as it is still just a model. It's an educated guess. The truncation error is simply the name we give to the difference between our simple polynomial and the true, probably way more complicated function that's out there in the real world. It's kind of a humble admission that our model is useful, but it's not perfect. So, after all this, why does it matter? What's the big takeaway? It's that with interpolation, we can take just a handful of data points and reconstruct a much bigger picture. We can tame wildly complex formulas, we can model real-world phenomena, and we can create those smooth, believable curves you see in every animated movie or video game. It's this fundamental tool that lets us connect the dots and see the hidden patterns that shape our world. And that kind of leaves us with a final, pretty powerful thought. We've seen that we can cook up a formula to perfectly fit almost any set of points we find. So if we have a tool that powerful, what are the limits? Is there anything we actually can't model?